Thank you so much for having me. I've been working on pollution and urban topics in LA and LA Long Beach area for a long time, and I've been here since I started that. So it's nice to actually, be boots on the ground finally. So what I'm going to talk about today is who benefits from air regulation policies. All right. So there's been some work on this done, and the evidence has been kind of mixed. So when we clean up air pollution, is it poor households benefiting? Is it rich households benefiting? There's some questions there. So one way we could look at this is, do housing rents respond as much as prices, house prices? If we clean up air pollution, neighborhood's nicer, house prices go up, but rents might also go up. There's it's kind of the newer, better evidence we have is that rents don't seem to go up as much as house prices, which in one sense is giving low-income renters a benefit, improved air quality, without them having to pay for it. But there's some other evidence that shows maybe rents do respond as much as house prices. So it's a little back and forth. At the same time, do low-income people or people in general, do they sort across space? When air quality changes? Does the demographic composition of a neighborhood change when the air quality changes? And we have a well-known study by Bonzoff and Walsh that says, yes, it does. People flow into an area after it is cleaned up. Whereas there are also, so this Curry, Davis, Greenstone, and Walker paper in the AR a couple of years ago says, actually, when we build a plant, it doesn't look like the demographics change very much. So what's going on here? There's a lot of quality research being done, it appears to find contradictory results. And one thing that might be leading to this confusion, or I'm going to argue, is that how we measure exposure to pollution matters a lot. So we have some source of pollution, it's going to infect households nearby. How do we rank those households from most polluted to least polluted? And this is something that it turns out causes a lot of problems if you don't do it right, and is a very complex issue. There are whole departments, it turns out, whole subsets of earth scientists, atmospheric scientists that devote their whole careers to this. And so far, we softer scientists, the economists and epidemiologists and so forth, have kind of just made things up as we've gone, and that turns out causes a lot of problems. And so what I'm going to do in this paper is bring some of those hard science methods to bear on this problem. I'm going to use much more accurate measures of pollution exposure, mapping each individual major polluter in the LA Long Beach area to every neighborhood to measure how does each facility impact every single neighborhood. And then I'm going to couple that with a natural experiment to look at how does cleaning up pollution across these different neighborhoods impact the demographic composition, rents. A separate paper does house prices that I'll bring in to compare to the rent changes to try to get an idea of who is benefiting the most from these pollution cleanups. Okay. And also, if time and interest permits, we'll do some residential sorting model to try to motivate the idea of motivate the welfare implications of when people leave neighborhoods after they get cleaned up. So results, just a brief snapshot before we get going. I actually do find that rents increase on par with house prices, almost to the dollar, which would imply that low-income households that are predominantly renters don't get this free lunch. They don't get the benefit without having to pay for it. I also find a large outflow of low-income households from cleaned up neighborhoods, which implies that they would have actually even preferred the cleanup to not have happened, which implies that they didn't benefit from it very much. And I also find that those households have very low rates of home ownership, which implies that they're moving because rents went up, not because they're responding to an increase in their wealth constraints, their budget constraints. They didn't just get a windfall from their house price going up and they're cashing out to move somewhere nicer. They're just getting priced out. Because all of this comes together to suggest that this air pollution cleanup tended to benefit higher income households more than low income households. So going forward, I'm going to talk a bit about this problem of measuring air pollution, because it's kind of critical to the contribution of the paper and understanding why we need to do the things we do. And then I'll go through the natural experiment that's probably a little more familiar to people in this room than the average place I present. Yeah?
Do you prefer we wait for questions?
Either way. If we want to just go throughout, that's probably be easier.
So, I mean, you're probably going to address this, but as you're talking about how difficult it is to actually measure the the actual improvement in air quality and bringing in these hard scientists who do that, I'm thinking, well, if that's the case, and just thinking of my own situation, many of these households don't know. So while your research is fine-tuning the data on the change in air quality, changes in house prices will reflect what households themselves are perceiving, and if there's a gap between the two, there may be a bit of a disconnect.
Yep. So it's hard to do it at scale. I'll put it that way. So if I want to know the pollution exposure to every house in California, that's difficult to do. If I find this one in this cute little neighborhood with a good school and I want to go check it out, and I go visit that house, it's very easy for me to determine if there are visible pollutants there. Now, if they're invisible pollutants, that's a whole different game, right? Particularly like ozone, carbon monoxide, things like that. But if there's coarse particulate matter or black carbon, things like that, and I show up to a house, I'm going to know pretty close. Now, I may not know exactly like, oh, this one is 34% more than this other house, but on average, law of averages, it's going to come out. In the paper where I look at explicitly the hedonics and the house prices, I actually do find massive responses, big changes to the house prices, with some suggested evidence that it's people responding to visible pollutants, that it's people going to visit houses and getting some signal about the air quality at those houses. So, but no, that's a very good point. But people are not running these models. They're not trying to find out what the exposure is everywhere like we are. They're just worried about the few houses they're going to shopping around at. So we'll go through natural experiment or standard Apple-style vertical sorting model, and then we'll go through the empirical results. So it's going to be a bit dry to start. I apologize, but stick with me. There will be a payoff. So the problem with measuring pollution exposure is that the methods we tend to use to try to get everybody are these. We use methods that have been borrowed into the social sciences from hard sciences. There's particular earth sciences like that we use for like rain forecasting right, that depend on the spatial covariance of the variable we're concerned about. So if it's raining right here, I've got a pretty good idea of whether or not it's raining 10 feet from here. And a less good idea, but still pretty good, about 100 feet, 1,000 feet, and so forth. And so you can use spatial interpolation, all sorts of advanced methods, kriging and so forth, to get an idea from limited monitors what the whole field of this variable looks like. And we've just borrowed those methods right into economics. The problem with that is that that's not how air pollution works. Air pollution isn't a natural process. It's generated by these, in essence, discrete points. So that if I know what the pollution is like right here, upwind of this smokestack, 50 feet away, I may have a very poor idea what's actually going on. So the spatial correlation, the spatial covariance of air pollution exposure as a variable is extremely complex and doesn't necessarily depend just on distance. It depends on all sorts of different things. And the nature of it is such that you're not guaranteed to solve that sort of measurement problem of interpolating, trying to just guess from a limited data set what pollution is. Even if you have a great natural experiment, a perfect natural experiment, it's not guaranteed to solve that problem. And I'll go through why that is in a minute. So to kind of walk through it, let's go to just a second semester metrics, diff and diff. We have a neighborhood and there's a polluter in the neighborhood. It's going to impact some outcome Y through both non-pollution effects, whatever they are, dependent solely on distance, and pollution exposure, which is going to be a function of distance and the wind and so on and so forth. Now, we're going to hit this firm with a shock. It's clean diff and diff. We're going to install a filter or a scrubber or something. It's going to lower pollution, but keep employment and output and so forth essentially the same. So in the geographic diff and diff, which has been used in a lot of contexts in crime and assessing school boundaries and so forth, we're going to draw an arbitrary line around the source. People close to the source are going to be treatment. People slightly further away but in the same neighborhood are going to be control. And we're going to take a difference between those two circles. And once we assign treatment and control, we're right back in a standard diff and diff model. This is going to be our treatment of interest, close times post, with controls for close and post. This is just standard diff and diff stuff. And graphically, this is what we're doing. We're taking the close guys, assuming they're exposed to the pollution, taking the difference with the control guys, and then taking the difference again over time, pre and post shock. Okay, very straightforward. Now the problem with this, right, is that pollution doesn't go in a nice perfect circle around a pollution source and then stop at this arbitrary line we've drawn in the sand. It looks more like this, where in the prevailing direction of the wind, that's where pollution goes, and it doesn't stop at any line that we've arbitrarily chosen. It just kind of goes on, tapers off forever, right? And so this is, I finally get to be, make this picture audience relevant. So this is the scatter regeneration plant just right over here by LAX. This is for 1999, and these circles here I've drawn at 1 mile and 2 miles, which are usually what people use for geographic diff and diffs. And you can see, right, if we were going to take the average exposure within the circle compared to the average exposure without, this is not a very good control group, right? In fact, the peak exposure is in the control group. And the lowest exposure in the whole sample area is actually in the treatment group, because these plumes are hot, they rise up in the air before they come down, and so actually if you're right next to the plant, you're actually maybe not so bad off. All right. This is a huge problem econometrically. So if we go back to our idealized little picture here, it's called the reduced Warmoth effect on these near guys downwind, x bar times beta, and we can write the effect on the downwind guys in terms of the farther away guys. We can write it in terms of this, right? So phi is just going to scale to make it so that, so if these guys get 50% of the pollution on average that the close ones get, phi is 0.5. If they get exactly the same, and it's just a constant, irregardless of distance, phi is equal to 1, okay? So when we take the difference across these circles, we get whatever non-pollution effect we haven't taken care of with our natural experiment, plus the true pollution effect over time times this wind bias, right? And the more the wind blows and carries more pollution into what's supposed to be our control group, phi is going to increase until it gets to 1, and we actually don't recover any of this true pollution effect, right? So if we have a perfect, clean, awesome natural experiment, we've controlled for all of the non-pollution effects the factory might have or the facility might have, we're going to get an estimated coefficient of 0 as wind speed increases. And so what happens if we don't have a perfect, clean natural experiment? Then we've very precisely recovered whatever those non-pollution effects are. And the only reason I bring this up is that actually there are a lot of studies in top journals, highly cited studies, that do exactly this. So if your natural experiment is building a facility, then obviously this is pre-construction of a major power plant and this is post-construction. You're not holding the non-pollution effects of that facility on the neighborhood constant over time, and you're going to get major impact, non-pollution impacts get wrapped up into your estimate. So that's the only reason I have this kind of extra baggage in here, because it is rather important given the state of the current literature. So this is in essence a contamination problem. So if we know the treatment intensity, the exposure intensity of all of these places, we can just rescale into two-stage least squares, and we're fine. Just like Miguel and Kremer in the deworming paper, it's just a standard econometric exercise. So why doesn't two-stage least squares solve this? Two-stage least squares would solve this. Why don't we just use pollution monitors to measure exposure and just get rid of this problem to begin with. And the problem is that monitors actually do a very poor job at large scale measuring houses. And so let's go through, and again, it's because of the spatial covariance problem. So let's go through this little example. We have a house, we have a polluting facility, and we have a monitor very close to the house. And we're trying to use the monitor to get a sense of what is happening at the house. Okay? So if the wind is blowing this way, all right, the house is getting inundated with pollution from the facility, but the monitor actually doesn't see any of that because it's upwind of the factory. So the pollution levels here and here are orthogonal. Monitor doesn't help us at all, regardless of how close it may be to the house. Same thing happens if the wind's blowing this way. Now we can kind of track what the firm is doing over time, which is nice, I guess, but it still tells us nothing about what's going on at the house. Right? If there's another firm upwind here, it could be dumping on the house, and we only get residual traces of that at the monitor, and we're still have no idea what's happening at the house. So the only thing that helps us, the only time that the monitor is going to help us out here is if it's right next to the house relative to the firm. If the firm splits the house and the monitor, we can't really use the monitor, but as long as there's no firm, there's no major pollution source between the house and the monitor, we can maybe do something with the monitor. Okay, yeah?
How are monitor locations decided?
It's a good question. Local regulators, there are some guidelines from the EPA, but it's kind of jointly done with the EPA and local regulators. Corbett Granger at Wisconsin has a great paper on that using satellite data to show that local regulators tend to put monitors in cleaner areas in the county to make it easier for them to comply with federal regulations. There are a whole host of monitors. I'm going to try not to get into it too much here, but yeah, monitors are not great for measuring like population exposure. And economists do it, epidemiologists do it, basically nobody else does it. So like the first time I started talking to people at EPA and NASA that do this kind of modeling, I said, oh, here's what we do. And they didn't laugh, but they were kind of slack-jawed aghast that anyone would do that because of these exact problems. So yeah. So let's just, taking all the, the endogeneity problems and people gaming the monitors, the placement of the monitors aside, just say we've happened to find these monitors, lucky us, we need data, that's all we care about. Let's just focus on the area around the monitors before we hit the firms and it causes a discontinuity in our spatial covariance. So this is Long Beach here, LA. These white dots here are monitors, and each of these little pink crosses is a major polluter, right? So the polluters outnumber the monitors something like 200 to 1, 400 to 1. And this is LA, right? LA County, here's the LA Orange County lines. If you want to use pollution monitors, this is like one of the best places in the US to do it, right? And so we've kind of got this area here, that area there, lots of problems. And if we actually look at, we use this in engineering model, I'll introduce it a little more thoroughly in a few slides, but if we map the exposure that comes out of every pipe, every pollution, or every polluter to all the areas around it, this is what we get, right? So here are our monitors. This is zoomed in a little bit. And you can see all of this spatial that the spatial variance of the pollution exposure is a few orders of magnitude more than we have monitors. So if we try to use these monitors to interpolate this field, it's like trying to interpolate a 100th order polynomial using a straight line. It's not going to happen. And instead, so you don't have to imagine it, I've gone ahead and done that interpolation for you. This is using the kind of standard operating procedure in the literature, inverse distance weighting, limiting to 15 kilometers away from the monitors. You can see how much variation we lose by doing this, right? And not only that, but it's also statistically misleading, right? Because even if you have 1 million households, all right, panel data, whatever, and you think, okay, I've got 1 million degrees of freedom, a million measures of pollution exposure, really you've got like 2. And in this area over here where you've only got one monitor within 15 kilometers, you've got 1 degree of freedom. You're putting all your eggs in this one basket when really the standard errors you're spitting out think you have like 1 million. Right, so if we do something a little more advanced than inverse distance weighting, we use Kriging, which actually tries to explicitly estimate the spatial covariance. It actually looks even worse. So the problem is not the method of interpolation. The problem is that we're trying to estimate a 100th order polynomial with 3 data points. Right? So
I think going back to Eric's question, though, first of all, I think this is great. I think improving on these measurements is very important. You recall that AQMD is testing mobile monitoring precisely because of that. But at the end of the day, when people buy houses when they do trades in the housing markets, most of the information that they would get on environmental outcomes, like what you're talking about here, probably comes from the monitors itself, because that's maybe the information that the general public has available to them. And so if these were to measure health outcomes, I would understand that actually improving the accuracy of measurement would go a long way to actually reflect proper exposure. But if the benefit here is going to be measured by changes in housing prices, how do we know that those changes in housing prices are actually reflecting what's happening in reality vis-a-vis the information that agents have when they do those transactions? And if that information is actually linked with what comes out of the monitors, why would I expect that what you're giving me here in terms of welfare measurements is actually improved over prior literature? Or is just other measurements that could have all kinds of problems as well?
yeah. So currently, CARB and AQMD, they have these like online portals where you can go and look at, what's the air quality like in this neighborhood, in your zip code or this neighborhood, and those certainly incorporate the monitors. They also, I don't know about CARB or South Coast specifically, but some of these portals also incorporate other information like the wind patterns and these dispersion models. So a lot of this dispersion model and this data and stuff I got from South Coast. So this is the stuff that they use. This is the stuff that EPA uses. That's also like currently. So this shock happened in, we're talking 1999, 2000, 2001. So there is no web portal to go on to look at. You can maybe look at local like smog alerts during the summer, like these other things, but mostly it's people that are going house hunting. They go to an open house, they go to view a place, and if it looks polluted, if the air's hazy, if they have a coughing fit, if it smells bad, they get a signal about the air quality. And the actual house prices is not going to be the focus of this paper. I'm going to touch on rents a little bit, but mostly I'm going to look at changes in demographic composition. And the fact that it's very comforting to me, like taking the totality of the evidence, that kind of skipping ahead to the results, house prices and rents from 2 totally different data sets at totally different kind of levels of aggregation lead to, within like 7%, 5%, the exact same number for marginal willingness to pay. And we see in those same neighborhoods sorting responses based on those price changes is exactly in line with theory. Now, are we capturing all of it still? Like, even given this visibility, there's probably still a lot of noise in the responses. There's probably, people might not be internalizing it. They might not be realizing, there could be, they could be doing a binary search, like everywhere that looks dirty to them at all, they assess as like kind of the same level of dirty, so they're not responding enough. There's definitely that, but knowing where people, ex post, knowing where things got cleaner and where people would have had this opportunity to update information, that's the improvement here. Yeah.
My sense about like what all gets captured in this head-on models in terms of value is that a lot of it will have to do not necessarily with the pollution directly, but with the intermediate effects between air pollution and the set of amenities that end up having in the neighborhood. I mean, we know from other literature there's lots of tipping points in the neighborhood composition of it. So my sense would be that it would be a combination, maybe yes, of the information that they could see from the website, which if you look at the website of air pollution in LA by neighborhood, it looks somewhere in between your two figures. Somewhere in between the super detail where you can see, you know, the pollution concentrated the source, and the more dispersed thing that we do in most economics papers. It's definitely not as precise as you're showing me. For example, you cannot see, for instance, the high level of air pollution near highways, right?
Yeah.
In those type of maps, right? Which we know it's quite problematic in LA area, right? But then you start thinking about, you know, like some people react to some people physical health will react to the air pollution that's there, whether or not they know about it, and perhaps they'll move out of the neighborhood and they'll start a path of changing the demographic composition and whatnot, and you know, and people will move where they find people like them, right? And so I think, you know, to me it's always a little bit hard to interpret. Do we think, to the extent that a lot of those effects go through demographic composition, do we think of those as representing the value that we get from air pollution?
Yeah, no, so that's a big problem with hedonics, right? That as soon as you change one thing, you potentially change everything. Right. And one defense against that I have here in this context is at least with, so I'm going to step back and not do the residential sorting paper, do the actual hedonic paper here, right? One kind of defense against that is that I have the actual sale house data, so we're not doing like a 1970 to 1980. I'm looking at like month to month, actual transactions. And so if you see, right, so if the price effect we see is kind of a gradual ramp up, then we're really worried about that. If what we see is like a drop in pollution and a corresponding spike in house prices, then most of that is going to be house prices. Now, you could say, well, people are kind of anticipating, the market is anticipating that we're going to get a Whole Foods in 5 years, right, once we're sufficiently white and yuppie in this neighborhood. It's possible the market is that good. If the market is that good, then they're probably also picking up the pollution stuff to begin with, and I'm kind of like spinning critiques around on myself now, or on you guys, I guess. But I find like the pollution concentration, I don't show it here, it's in the other paper, but you look at the pollution concentration at the house level and the transactions, and they're like a perfect mirror image, even over like a few months. So that's one case really mitigating that. So, so I don't think I started in on this slide at all. So the econometric problem, sorry to get back to the boring econometric stuff, but also I'm not sorry. The over-smoothing problem we have here actually leads to severe non-classical measurement error, which is actually not a problem with our IV, using the IV to filter out that measurement error and the subsequent attenuation bias. The problem arises is if the IV and the measurement error are correlated, right? So let's say you're using this geographic diff and diff as your instrument, and your instrument is close to a firm, right? Looking back at this picture, where is the measurement error going to be the biggest here? In the high exposure areas right downwind of the firm, right? So almost by construction, your instrument and the measurement error are correlated. Even more easily to see is if you use the Clean Air Act at the county level, right? Because the Clean Air Act is specifically targeting monitor averages, not exposure averages, right? And you can go through the econometrics, but it's very easy to show that that's going to lead to a 2 safety square estimate that's downward biased when you use the Clean Air Act as a natural experiment and use the monitors to measure exposure. And more generally, this problem of using monitors, I have kind of talked about it already a lot, using monitors to measure pollution exposure to the population is hugely problematic, right? So go through the exercise of you have a county, and those people are allocated in some way. The pollution is allocated in some different way based on wind patterns and where firms set up shop. And you, in that snapshot, you know exactly what everybody's exposure is, and you're able to place the monitor at exactly the median, the population median. So on January 1st, 2015, you know that that monitor corresponds to the population exposure median. Fast forward 1 year later, people have moved, firm behavior has changed, maybe the wind's blowing a slightly different direction. How does that monitor correspond to the population exposure distribution now? 35th percentile, 60th percentile, who knows, right? There are these three spatial distributions you have to worry about: population, pollution, and the monitors, and they are not necessarily linked in any way, and certainly not structurally. If you look at the map of monitors in LA, they form like two arcs as you go further inland, right? They're clearly not aligned to try to pick out, so that the average of all those monitors corresponds to the average exposure in the county. It's some weird, pretty, I mean, it looks pretty, it does, but what does that tell us about population exposure? Who knows? And what's more is you can actually see there's some glimmers of evidence from past literature not considering this problem at all. There's some glimmers of this problem peeking through in this past literature. So there's a Niddle, Miller, and Sanders paper where they actually say, hey, is there non-classical measurement error in our spatial interpolations of these monitors? And they find overwhelmingly, yeah, there's huge non-classical measurement error. It's consistent with is over-smoothing. Another paper, this Carlson and Zebarth, who aren't necessarily looking at this problem per se, but they also do spatial interpolation with monitors, trying to get health outcomes, and they do this standard cross-validation to try to measure the quality of the interpolation. So with that, you have 3 monitors. You interpolate between these two to try to predict the value of this middle monitor without actually using that monitor. And this goes back to Janet Curry and Matt Nidell in 2005 started doing this, and then you use the predicted value and the actual value, measure the raw correlation, and the closer it is to 1, the more comfortable we feel with this interpolation method. Now the issue is that raw correlation doesn't take into account any temporal variation that's common to all monitors, right? So imagine that a monitor, or that at a physical point in space and time, there's a fixed spatial component that never changes, and then there's a common temporal component that changes uniformly across everywhere. And that the spatial components are actually IID, they're independent. If I know the fixed pollution, the average pollution over 10 years here, it tells me nothing about the average pollution over here, right? If I do this cross-validation measure and take the raw correlation, I'll actually find a positive spatial correlation coefficient. Whereas if I take out the temporal trends, I'll get the correct answer of 0 spatial correlation. All right? And so this Carlson and Zebarth, they actually do this exercise. They do the raw correlation. They do their cross-validation and say, hey, our NO2 interpolations, we have a correlation coefficient of like 0.9, 0.95. This looks really good. Once we take out season fixed effects and year fixed effects, they go down to 0.1, 0.15. All right. So long story short is the monitors are not going to fix this problem of knowing the exposure intensity that we can use in 2 least squares. So after the doom and gloom, what should we actually do? Well, in this paper, I'm going to use an atmospheric dispersion model, which uses the work of atmospheric chemists and physicists to predict, given wind conditions and temperature and barometric pressure and so forth, once a puff of gas comes out of a smokestack, where does it go? Right? And then we can take that prediction, sum it across all firms, and get the total exposure to industrial pollutants, or in this case NO2, industrial NO2, at any point in space and time. Okay, so and this has been vetted pretty thoroughly by actual atmospheric chemists. What they'll do is they'll go to different scenarios. A dense, urban, windy, hilly place. Flat, rural, all sorts of different scenarios. They'll let out a tracer chemical that doesn't exist otherwise in that area. They'll lay out a network of monitors every 100 meters or so. They'll let out the tracer, they'll let it go for a while, they'll measure it with these monitors, and then they'll compare it to their predicted model tweak it, refine it, and they find that it does really, really well. I've found in presenting these papers that that's not at all convincing to economists. So what I do here is actually take the two monitors I do have in my sample area and plot over time the prediction here in blue and the actual monitor reading in red, right? And I restrict it to fourth quarter of the year because there are some chemical transformation problems. So if there's NO2 comes out of the pipe in quarter 4, I know it's staying NO2 as opposed to turning into ozone or so forth. And you can see is that it does pretty well.
But wait, doesn't that model use the monitor's data
No.
itself? No? Okay.
Nope. It uses measures of what comes out of the pipe, the size of the pipe, the height of the pipe, the smokestack, and then it uses wind patterns. Yeah, it doesn't use monitors. Yeah, so that's a huge problem, right? And that happens with satellite data sometimes. That the satellite data are ground truth to the monitors, and you say, hey, they predict the monitors really well, but that's by construction. No, this is not by construction. This is data generation A, data generation B, totally distinct and separate, and we bring them together, and they look like this, which I feel like this is cheating, doing like physical chemistry stuff and making it look this pretty.
In fact, a lot of the work that then atmospheric science end up doing is the calibration, because often they just don't match at all.
Yeah.
In that dimension.
Yeah. So yeah, the margins that these guys are now working on, right, are like, you know, accounting for building downdrafts and how reflective is the surface of the Earth with, you know, solar radiation and things like that. They're like orders of, you know, fifth order stuff to us, and we're over here, you know, throwing rocks around basically when it comes to this, but comparative advantage, right? So the last bit on house prices I'm going to do to show like how much does this really matter, this using these kind of more precise methods. So if I use a uniform dispersion, assume it just kind of goes in a circle, and replicate the methodology of Bonzoff and Walsh in the 2008 AER paper, and measure the effect of my natural experiment, which I'll talk about in just 2 slides. This is what I get, the impact on house prices. So come through here, a big shock, a big drop in air pollution after 2000, and it doesn't show up at all in house prices, which is consistent with, somewhat consistent with what we find in the literature. It's just not very big house price responses. Now, if I use this more precise method of measuring air pollution exposure, this is what I find, right? Basically flat until the shock, and then it spikes up. All right, but this is the other paper. This is just kind of like lend credibility to the importance of this methodology. And if we look at the effect of the crisis on the average house price and the corresponding marginal willingness to pay, we get something that's an order of magnitude bigger than past estimates, or estimates replicating that past methodology, that conventional methodology on this same data in the same experimental framework. Right. So let's actually talk about this natural experiment that I'm going to use on these neighborhood level outcomes. So what I'm going to use is the combination of reclaim and the California electricity crisis of 2000. So in 1994, after the Clean Air Act amendments of 1993, regulators were given the authority to basically do whatever they had to do to get air pollution under control in California. And that included instituting cap and trade programs. And so South Coast Air Quality Management District instituted reclaim. There was a cap and trade market for NOx and SOx, where at the beginning of the program, firms were given 100 permits for 1994, 80 permits for 1995, and so on and so forth through, I think, like 2020 or 2030. Right? Permits couldn't be banked. You had to use them in that year. So if you didn't use the permit or you didn't sell it, you just basically threw it in the ocean. Right? And so what happened was, to start this out so they didn't crash the local economy all at once, the cap was very loose. I think there were twice as many permits as there needed to be in 1995 when the program actually started, or 1994, and was set to slowly ratchet down, but in a fully known ahead of time way, so it would become roughly binding around the year 2000. Or that's how it worked out, given firms' response or non-response in the mid-90s. So what happened is that firms played this gave us this great example for like Econ 101, not internalizing other people's decisions. And they said, well, I've got tons of permits, and nobody's trading permits, and so the permit price is basically zero. And in 3-4 years, when I run out of permits, I can just go on the market and buy them for almost nothing. So I'm not going to do anything, right? And they played this game not realizing that everybody else was also playing this game, and that when the hammer came to drop, everyone was going to go try to buy permits all at the same time, and there was going to be no permits to be had. And that's exactly what happened in the summer of 2000 when the California electricity crisis hit, and local generators, the municipal generators that didn't go out of business, ramped up electricity. They were bringing in boilers out of mothballs, to my understanding. Their NOx emissions went through the roof. I think it was a 4-time, like a 300% increase. And they started buying up permits like crazy. And very quickly, halfway through the year 2000, everyone else realized, oh my gosh, there's not going to be enough permits to cover NOx emissions at all. So almost immediately, the non-electric firms started to cut emissions, started installing abatement technology, started shifting production across to more efficient boilers, and you see a drop almost immediately in the emissions. So this red line here is the emissions at the average electricity generating plant in South Coast. You see it spike up in 2000, then eventually drop down, and they end up at about 50% of their original NOx output. This blue line is the non-electricity generating people, and you see them kind of bounce around, kind of carefree, not a care in the world, and then 2000 hits, and they go off a cliff. All right? And so this sudden drop is the exogenous variation in pollution exposure that I'm going to use. And what we're essentially going to be doing is rolling a diff and diff backwards. Instead of starting at parity and separating people into exposure, non-exposure, we're taking people in exposure and non-exposure and bringing them closer back to parity, right? So the instrument I'm going to use is this pre-period exposure. It's a measure of basically how downwind are you from a large plant before the program starts, interacted with a post dummy for after the shock. So we'll use that to look at the outcomes in these various communities. But before we get there, I want to talk a little bit about this residential sorting model that's going to motivate how do we interpret these moves we see people make across communities. So, and this is a standard EPEL vertical sorting model. I'll make a small addition to it at the end, but for the non-urban economists here, I'll go through this very quickly. So, model consists of communities and households. There are J communities that are defined by some exogenous amenity, G, so places closer to the beach have a higher G, places further away have a lower G. In this case, it's going to be air quality, higher G, cleaner air, lower G, worse air. Totally exogenous to the community. The community can't decide what its air quality is because it's blowing in from somewhere else. It's a decision-making process larger than the neighborhood itself. But the house prices in that community are going to be endogenously determined depending on how people sort across communities. Households are going to maximize some indirect utility that depends on an exogenous income that doesn't depend on where they live. But then they're also going to pay for housing and consume amenities wherever they end up choosing to live. And an equilibrium here is going to be an allocation of households to communities such that nobody wants to move. Right, pretty standard definition of equilibrium. Now, the real contribution of these EPEL and co-author papers is that they are able to characterize this equilibrium and say that if it exists, the equilibrium is going to be such that the poor households live in the lower amenity communities and house prices will be lower, and they will basically vertically sort from lowest income, lowest amenities to highest income, highest amenities, and highest prices. And it will be such that there's a boundary difference and that housing supply equals housing demand. So what we get from that is, let's say we have just 2 cities, and we line up all the households, poorest to richest, and say, okay, these are the guys that live in city 1, or these are the households that choose to live in city 1. These are the ones that choose to live in city 2. There's going to be some household here on the boundary that is perfectly indifferent between the 2 households, and we can use that household to do comparative statics and measure what's going to happen if we change anything in the system. So let's say we make the air quality a little bit better in city 2. Well, this indifferent guy is going to say, well, I was indifferent before. Things got better in this city. I'm going to move over there. And the next household here is going to make the same decision, bidding up prices here, bidding up prices in city 2, bidding down prices in city 1, or the prices going down in city 1. And that flow out of city 1 into city 2 is going to continue until prices increase enough in city 2 that the flow stops and we get some new and different household here in the middle. Okay? And we can use this difference to track all sorts of things. That's really the margin we care about, is how many people are moving, how quickly, how sensitive are these households to the changes in air pollution. And we can back out the amenity values from that.
Is there reason to believe that some demographic variables, so household variables, characteristics other than income might be decisive?
Oh, certainly. So like number of kids is the big one.
Exactly what
Yeah.
I'm thinking.
Yeah.
Right? And to the extent that maybe on a life cycle income kind of perspective, it may be that families with young children are also sort of early in their income earning stage, and so is that something you account for?
So you can generalize this to include not just income, but a amenity preference parameter that could capture that, or even just the fact that maybe I don't care about my lungs, or maybe I don't care about the beach, or any of these other things.
Just some people care more than others do.
Right, exactly.
And to the extent that's correlated one way or the other with income, and those demographic variables are not included, then income is in a sense absorbing the workload of that.
Right. So this is not a structural model I'm going to estimate. This is a to inform us basically how to interpret the results we get to at the end, because they're kind of squirrely.
Right.
And this is not me. So far I've contributed nothing. This is like canonical 1980s urban theory here. I think the more recent, the generalization is Eppel and Sieg 1999, where you get this really cool space where you have income on one axis, and so instead of a line, you have R2, and you get these sort of they look like indifference curves, but you basically get a curve that's a boundary instead of a single point. But it can be generalized. I'm not going to do it here, because what I'm about to do, the innovation I'm going to make, is to point out the problem here, right? Is if I improve city 2, it's only got one endogenous boundary. The only thing that can happen is people can move in or they can move out. There's nowhere for these guys to go. And if I change city 1, there's nowhere for these guys to go. So the poorest person here is always going to live in city 1, and the richest household is always going to live in city 2. Right? But in reality, and in these models even that generalize to J cities, there's almost always going to be somewhere to go both above and below. So what I'm going to do is, when I do the comparative statics, I'm just going to generalize to 3 cities, or I'm going to specify 3 cities instead of 2. So that I get at least one place that has 2 endogenous boundaries. So if I shock city 2, people could come in, people could go out, people could come in, people go out. And so kind of walking through, you're coming from the 2-city model, you might think, all right, I shock city 2, people are going to come in from the top and the bottom, right? That's the kind of natural inclination. Population flows in to the city when it improves. That's what Bonzoff and Walsh 2008 find. That's kind of that's the basic T-BOO intuition. But if we have increasing marginal willingness to pay for the amenity, or if we have single crossing, which is what we need to get this kind of stratified equilibrium, the people coming in from the top are going to bid up the amenity, the same amenity change, faster than the people coming in from the bottom. So the people aren't going to flow in as fast from the bottom. And in fact, if the people at the top bid it up high enough, nobody may come in from the bottom. In fact, people here, incumbents, may leave out the bottom. And that's really the result we're worried about, because it has all sorts of like welfare and equity implications, right? So think about the weird welfare implications, right? If people actually get to vote on the amenity change, it's not exogenous.
It's a kind of gentrification phenomenon.
That's exactly what it is. That's exactly what it is, where you go to people ex ante and say, would you like to improve the air quality in your neighborhood, or would you like to improve the school quality in your neighborhood, whatever this amenity is, and they say, no, thank you. In fact, I'll pay you to keep it dirty.
Right.
to some degree, because I've already shown through revealed preference that I like this city better than that one. And so if you raise prices here, even if you raise the amenity, I'm going to have to go to the second choice, and you've made me categorically worse off. So this leaving is what we're going to be looking for here, all right? And the fact that potentially, just based on kind of the Pareto distribution of income, if the rich guy bids this up enough, he might push out 2 households. And actually you get instead of the nice places becoming dense, as you might expect in Tibu, it actually become less dense, which, spoiler, that's what ends up happening. So empirical results. Questions we're going to try to answer: do rent increase as much as house prices, using the house price results from this other paper? Do low-income people get pushed out? Do we observe any of this displacement? And do low-income people own their own homes? That would actually mitigate the displacement problem and make it welfare, ambiguous. So data, this is, by my own admission, I would argue the biggest shortcoming of this paper. I'm using census and ACS data at the block group, so I can see net flows, but I can't see gross flows. I can't see if people move from one block group to the, so if 2 different low-income households switch, it's going to look like nothing happened, which is a huge drawback here, and it's the main reason why I didn't actually try to estimate a more robust kind of structural model, because it just can't be done with this data. But we can glean quite a bit from these net flows. The other data are pretty straightforward. The emissions data are admin data from South Coast used in enforcing the cap and trade. They actually have monitors in these pipes that report in real time back to South Coast. So this is as real as it gets as far as what's coming out of the pipe. Firm equipment coming from the NEI. This is how tall the smokestack is, the temperature of the gas coming out of the smokestack. Both of those components we need to do our atmospheric dispersion modeling to know what exposure is around each firm. And then atmospheric data also come from South Coast. They have these network of monitors laid out specifically to use with this atmospheric dispersion modeling. So to start with kind of some summary figures, let's just look at how stratified things really are. So this is a bin scatter, 20 bins along the horizontal axis, and then the average of each bin, not a decile, but a 20th cile, whatever that is, average within those bins. And what you can see, right, is that Tibu actually does pretty well here, or the vertical sorting does really well. There's obviously some other sort of amenities here that aren't being accounted for. If you look at the picture and you kind of know LA, there are basically 3 variables, as far as I can tell, that explain this. Pollution, beach access, and are you Compton or not? And that's basically it. Because Compton, it turns out, doesn't have a lot of industrial pollution, but it has other disamenities, I understand, that may not lead to yuppieism and gentrification and so forth. So that's pretty stratified. Same if we look at exposure and median rent. There's a little jump up there, but again, it looks pretty stratified. So Tibu's doing pretty well here. Epple and Sieg are doing pretty well, but also this underlines the fact that we can't just go out and estimate this OLS. We need some sort of exogenous shock. We need some sort of really credible instrument to be able to disentangle this from the actual pollution effect. So this is the estimation equation I'm going to use. Various outcomes we'll look at. Let's call representative Y for now. There's air mod measure of exposure that to get at this, try to get as much at this population problem, what I do is I predict to the center of each census block, and then I weight up to the block group based on population. So this is like a population-weighted average within the block group. A fixed effect for each block group, which turns this in the 2 time period since essentially turns into a first difference. Post control, and then a bunch of time trend controls based on your year 2000 level of any outcome we might be looking at. So the race and ethnicity composition of your neighborhood in 2000, the income by bins, the population, the education by bins, and then an additional sort of city level effect below the metro that's just an arbitrary 10-kilometer grid to get around discontinuous city boundaries and unincorporated areas and so forth. So, and then the instrument I already talked about. I'm going to use this AirMod pre interacted with post to instrument for this endogenous pollution exposure variable. So first outcome we'll look at is rents. Now this is straight from the census. It's really bad. It turns out rent data in the census is really bad. Something like a third of it is missing, even in areas where you can look on the map and there are renters. It's a lot of missing. But all told, we still actually find pretty consistent results. So the interpretation of this second stage here is that 1 microgram per cubic meter increase in your neighborhood of NOx emissions leads to a decrease in rents of about 1.3%.
This is an effective crisis on rent costs. This is a shock you're modeling, right?
Yeah. So the instrument is a
crisis.
Yeah. So that's the electricity crisis, right? So this AirMod pre is going to measure your exposure to the crisis, how intensely the crisis impacted your air quality in your neighborhood, and then we use that pre-post to instrument with this continuous. So in the second stage, it's a semi-elasticity. In the first stage, it's a variable intensity diff and diff. So the crisis increased rents by 0.3 percentage points per unit of exposure, or per unit of treatment intensity, which was an average of 6.5. So increased rents by like 4% on average. And then the semi-elasticity is there. There's not much context here to compare. What we're mostly looking for, right? Because this isn't so much a hedonic. We're not trying to measure the size of the pie. We're trying to measure who got relatively more of the pie, right? This other paper this paper builds a lot on actually does the size of the pie estimate. So if we go and look at what happened to house prices, what happened to rents, we find that basically that they're moving together very, very closely.
Did you try to do this without so if I understood correctly, the way you calculate the exposure has involves some population weights? Is that what you said?
Sort of. So the variables I want are at the block group level, right? And so if the model I have says you give me a point in space and I'll tell you what the concentration is at that point, right? So the question becomes, how do I represent a two-dimensional figure, this block group shape, using a single point? Do I take the center of the block group? Do I take the population-weighted center? Or do I try to mix both of those and say, integrate, take the expected average weighting by population over the whole block group? And that's essentially what I've tried to do. So I take the center of each constituent block within the block group.
So let me see if I understand correctly. Sorry about it.
Yeah, this is into the weeds.
So you have a couple. So this essentially like a couple of monitors, a couple of points, not monitors, but a couple of points within the block where you have the data.
Yeah. So I can get the concentration with this model. I can get it at any point I want. So instead of taking the center of the block group, I've taken the center of each block within the block group, and then averaged those weighting by population. So let's say there are 2 blocks within the block group. One has 1,000 people and one has 2.
Yeah. So yeah. Then then I think my concern applies to this. So my concern is that now there's some sort of measure of density embedded in your air pollution measure. Right? So, to some extent?
I mean, sort of. It's a
I guess it adds up to. Anyways, so let me tell you what my concern is. And maybe it's not an issue.
Yeah.
But my concern is that that density is also going to be reflective of how tight the housing market is. And I'm just worried that somehow that those weights are going to react. The density of how prices react to pollution, right? Is correlated with how much density there was there to begin with, right? It might not be an issue because now I'm thinking that if you're weighting, if the weights add up to 1 in each unit, right? Then it might not be an issue, but let me think a little bit more about that.
So this
different ways of maybe just
Yeah.
averaging, maybe just getting that and just averaging.
So this is the weights are only going into this variable here.
Right. Yeah.
Yeah.
That's my concern. That's the endogenous variable. That's the one that you're going to.
Right.
to
So,
instrument. And my concern is that the population densities embedded in that are going to react to your instrument.
I see. So, this, I think I'm using year 2000 population densities here. So I'm not. So it's not doing like year by year the densities are changing. It's I take a fixed density. Just to, so instead of if I have my block group, instead of taking this point, if I know more people live over here, I want to take like this point. That's all this is doing. It's not adapting. So if everybody like leaves and moves over here, the point's not moving. That could potentially be a problem. The other thing is with the house price, with actual house price regressions, there is no weighting. I take the exact point of the house.
Okay, perfect.
Yeah, this is just.
That was weird.
Okay, sorry. I should have gone straight there. I'm sorry. Yeah, or I'm kind of. We're doing both papers at once here, basically, I guess, because the machinery. I can't do the second. You can't do the sequel without people knowing the first one, I guess. So, yeah. So yeah, what we find, despite the weighting and despite the two different data sets and the terrible rent data in the census, we get almost to the dollar, the same marginal willingness to pay, same aggregate, percentage response of the crisis to rents versus house prices. So renters, it doesn't look like renters are getting a free lunch. The prices responding accordingly. That if they want to consume these better amenities, they have to pay for it. So now let's look at demographics. I'm going to run this exact same regression again for each of these outcomes. All right, so this is the log median income within each block group, the log population, log number of households, and because this is kind of a first difference regression, I use all these logs that basically do a percentage difference. So that's how you interpret this, yeah.
Yeah, so just thinking about the rental effect being similar to the home price effect, should we be surprised by that in areas where there's substantial rent control? Like, would you expect to see differential effects there?
Yeah, with substantial rent control, no, you shouldn't. Right? If the rents can't go up, then no.
Which almost makes it surprising to me that you're finding the same effect.
Was there substantial rent control in LA at this time?
I'm under the impression there's not.
No, I didn't.
I thought that
At this time, yeah, like San Francisco, New York.
things were built pre-67 or 75 or whatever it was. Like, everybody I know in West Hollywood is under rent control.
Huh. I'll have to look into that.
Maybe there's not a big enough population to get an effect.
Yeah.
I don't know. I mean, this is just like very casual, but I mean, I've been living here 30 years, and rent control almost never comes up in discussions I hear. Whereas, in New York, where I don't live, I go there and these kinds of conversations come up all the time. So
this is like.
blissfully unaware of rent
at this point, New York, San Francisco, Massachusetts got rid of rent control in '95, I think, and I think outside of that, it's not.
So there are still units here that are So there exists a year.
I'll have to look into that.
It's rent controlled if you're before that year.
I'll have to look into
I
that.
guess I've got so almost like the inverse of maybe the same question in a sense. I mean, just on the basis of first principles, why wouldn't we expect any changes in rent attributable to a positive or negative shock in air quality to be capitalized in the underlying house prices? I mean, I would think.
So you think they should move together, right?
Yes,
when we think
of first principles to the extent that generally, I mean, this is what I teach to my students. Maybe you'll tell me, inform me that I should do differently. But I essentially argue to my students that rent essentially represents the sort of conditions on the ground now, right? And that I do a kind of a triangle, right? There are financial markets out there that are sort of fly above all of this stuff that generate average return rates of returns to assets, and housing, the real estate market is essentially is juxtaposed between these on the ground experience of what people are willing to pay on a month by month or year by year basis. And people who are investing in housing are essentially juxtaposed between those financial markets and these rental markets, and that housing outcomes are in effect a direct or kind of the endogenous variable within that triangular configuration. And so based on that kind of first principles approach, I think Yes, of course they're going to be capitalized in it. So the fact that we see confirmation of that, I'm just wondering, why would we have expected to see? Why would we expect to see anything different?
So one reason, right, is that very credible people have found that there is this discrepancy in this other context. Now the question is that, are we now comparing apples to oranges by looking at two different sets of data? Are we looking at, is there that measurement problem with the pollution? I don't.
My view on that is expectations, right? That that what we pay on a month by month or year by year basis is what we're experiencing this month. To the extent that the people who are investing in housing, I mean, one thing of course is it's chunky, you know, to get in and out of housing market. So you're going to have that but then you also have the fact that you're doing your present value calculations over a much longer time horizon, and therefore there's more uncertainty introduced.
So I would argue that so as long as there's not a big inframarginal gap between substituting between renting and owning.
Which gap?
So let's say I have a house and I've divvied this house up into 3 units and I'm renting all those units. I'm owning, I'm the landlord, but it's very easy to convert that back into a single family home and sell it off to somebody to do owner occupancy. If that's the case, right, then they should track perfectly, because if some gentrifier yuppie comes to me and says, I'll pay you $500,000 for that house that you previously have been renting as, at the rate as though it was worth 250, then I go to my renters and say, hey, your rent was 500. When your lease comes up, I want 1,000 or you're out and I'm selling to this guy, right? Which is another argument for this moving together. Now you could get this separation if, for instance, there are segmented housing markets. So if it's really hard to convert, so if I've got an apartment building, right, I'm not going to convert that to a single family home. I could convert it maybe to condos, I could do something else, or if the population is sufficiently kind of bimodal, not bimodal, but if these people, if the gentrifiers are not interested in buying my house in Linwood or Compton or wherever, then that response is not going to happen. If the marginal person coming in is not a potential owner, then they're not going to track.
This is interesting, and I apologize to everybody if my questions are too simple, but if I understand you correctly, there are these kinds of reasons for thinking there might be a divergence between the rent differentials and this, but there might also be a reason to think that those are captured in the fixed part, right? So the differences somehow gets rid of those. That on the margin, when you're looking at a change in air quality, those other considerations that might create a wedge between sort of the rent flow and the capitalized value thereof are not. It doesn't apply on that amenity margin so much as it applies, in the fundamental relationship between rents and housing prices in a place for the reasons you're describing.
Potentially, yeah. No, that's potential. I think the main thing, right, is the marginal guy. So if I clean up the air in Compton a lot, and there's still the marginal guy is not the one from Palos Verdes trying to gentrify, then the response is going to be very different than if he is the marginal guy, right? If he is the one driving that price change. But that's kind of running out. I'd love to talk about this more, but I've got a few more slides here to get through. So actually, I don't think I've even talked about these results yet. So what I find here, right, is that these are just OLS with controls. It's all muddy and gross. If we look at the actual shock, the reduced form, we see that in areas that got a bigger cleanup, population went down, the number of households went down, the number of housing units went down, and the fraction of people in low-income households went down and shifted to higher-income households. Now, that only really makes sense, right, if we get this one rich person in, 2 rich people out. And if we had just gone straight to the two-stage least squares and said, oh, what's the impact of this study, we actually get reverse results, right? Because increased air pollution is leading to increased density. People are flowing in. That's backward. That's exactly backwards from TBU. But this is actually all consistent with this. It is consistent with the vertical sorting model, but we have to account for the fact that people might be leaving. And if we then...
So I have to make a comment on that.
Yeah.
Which I think is the point that that we made in the restart paper. Remember that the cleanups happen in a very specific way and with very specific goals, which is for you to be in attainment with the Clean Air Act, all monitors in your county need to be conformity with the standard. And so by default, you're actually channeling a lot of cleanups to the areas that were a lot dirtier to begin with. And I think that explains a lot of the dynamics that you're seeing there. These are not random cleanups. These are these are cleanups in really, unfortunately at this time, in really bad areas. And so a lot of this, for a huge sorting to take place, you would also have to convince us that a lot of the other amenities that individuals at higher income would value would be there, and they are not there. So I think there may be sorting happening, but I do think that this is all driven by the provisions of the Clean Air Act forcing certain types of specific cleanups that are quite concentrated. Right?
Yeah. So this isn't actually keying off attainment, non-attainment of the Clean Air Act, but it's the same effect. You're right. It's the same effect because you can't.
Reclaim was Southern California way of dealing with attainment status for NOx. Clean Air Act, the EPA says, you Southern California do whatever you want. I don't care. All I care is that you get in attainment with the standard. They implemented this program, but by default, and if you actually, if you look at where they were doing the cleanups, they were happening in a really, really bad neighborhood.
Where's my map here? Yeah. So I mean, even by construction, right? This is actually, I think it's with the Clean Air Act, that's certainly true. So this isn't. So these are not targeting specific areas, right? Because this is just on the market. But let's say we took all this pollution and we just wiped it out completely. We went just absolutely, there's zero NOx anywhere in the area. The places with the highest exposure are going to have the biggest cleanup. So that's effectively then a targeted cleanup. So that's something to think about. So if we break down the actual population changes by, is it poor people, middle income people, or high income people leaving, we actually find it's predominantly poor people leaving these neighborhoods. And that's on, again, that's on net. So there could be a lot of swapping going around, but on net, out of the whole sample area, we lose a ton of these low-income households. And if it comes out to, I think, 11 or 12% of all of the pre-crisis low-income households left as a response to this. A lot more left over that same time period, but I think twice as many as that left over the same time period for just aggregate reasons. Half of them left specifically because of this price increase due to this pollution cleanup. Now, if we break down, right, was it initially poor households, initially middle-income households, initially high-income households, right? We actually do find that all the action is coming from the low-income neighborhoods, right? So it's low-income people in low-income neighborhoods that are the ones leaving, right? And now there is some variation, like if we don't do the bin scatter, we do like the full scatter, we do actually have some richer areas that are also cleaned up. So it's not, we don't have this like segmented treatment. It's not that bad. But as far as the sorting goes, it appears that it's all happening, which based on the theory is actually what we'd expect to find, right? Because you need this large difference between the people coming in and the people at the top and the people at the bottom. And if everybody's already super rich and they can afford these margins, then they're going to be much less likely to flee the improved amenity, conditional on preferences, right? Anyway, sorry, was there another question on this here? I actually, yeah.
To Antonio's point about if there's not the other amenities there that sort of the high-income households would want, it looks like in your third column, the number of households, they're from low income is being replaced by the mid income. So it's not rich people moving into poor neighborhoods. It's middle income people.
So this isn't replacement here. This is if you started out middle income, your net number of households actually increases. So if your neighborhood starts at middle income, you actually get a net increase. People aren't leaving; they're coming in, and nobody's getting pushed out. Right? Yeah. No, this is a lot of numbers. I get lost in it occasionally myself. So, yeah. And this is open invitation. I don't know if this is kosher or not, but if anybody does have micro data on this area with like renters and things, I'd be more than happy to talk because I would love to actually get at estimate the full demand function, the full welfare, to see where are these people going, how much gross movement is there, to try to disentangle a lot of this. And that's one thing I have. I would very much like to do with this is to bring in a couple other amenities and see what other kind of interactions are going. That's probably the other big weakness with this paper. So finally, all this fleeing could be, if we get a little idealistic and say, well, what if all these very poor people actually own their houses by some weird stroke, and they're actually not responding to increased rents, but they just made a ton of money by their house going up $10,000, $20,000, $50,000, and now they're re-optimizing based on their new budget constraint. That could very well be the case. So this is a plot by your median house, the median income in your block group on home ownership rate. And what we find, maybe unsurprisingly, is that poor neighborhoods don't have a lot of owner occupiers, very few in fact. So at the low end, it's about 10%. At the high end, it's approaching 100% owner occupation. So now if we step back and say, let's say that the rents or house prices actually capture all of the change. There's no inframarginal people. This is a perfect like Rosen Roback. Everybody's marginal, and house prices capture everything. All right. What's the per capita gain based on how much pollution you got cleaned up versus how many people are living there and so forth? What's the per capita gain from this shock if everybody owns their house and the prices capture everything? That's this blue dashed line here. And actually, this makes it look like things are pretty progressive here, right? The poorer households do get slightly bigger cleanups, right? Going down to and decreasing with income. However, once you say, okay, everything's going to the property owners, so the people that live there that don't own, they get nothing because rents go up to capture exactly the benefits of the amenity. Once we take into account of that, we get this red line here. And it actually, because of this such low home ownership rates, the poor individuals are actually not getting much of anything. Now, this is obviously not what's happening. There's inframarginal people. There are poor renters that see their rents go up 20%. They say, you know what, my kid has asthma, and we like it here anyway, we're staying. So this is a very kind of idealized case, but it gives you an idea of how little the home ownership is actually operating as a mechanism of allocating benefits from this program. So finally, in conclusion, we see these large rent increases, see people flowing out en masse, and see very little home ownership among these low-income neighborhoods. All points to suggest, you don't want to be conclusive here because there's a lot of moving parts in this, but it definitely suggests that this is not a terribly progressive program. As far as if we're thinking about the equity of improving air quality, there are some maybe concerns. So, yeah. And that's all I have. Thank you.